Thanks for the introduction. Glad to share some of our recent research in federated learning here at the FedVision Workshop at CVPR. So let's get started. As we know, federated learning is one kind of decentralized learning, where these clients will collaboratively jointly learn a model without sharing their data between each other or with the server. And in most of this talk, we will consider federated learning in a cross-device setting where the clients are mobile devices. And this kind of federated learning has been applied in practice. As you may know that at Google, there are quite a few applications are trained by federated learning. Specifically in Android 12, there are a few like Gboard applications and Google Health Studies and some other applications that use federated learning techniques to protect users' privacy. In the first part of this talk, I will talk about techniques for federated learning with formal differential privacy guarantees. The algorithm we described is primarily based on the ICML paper last year. We have open source code for that. And since then, we have been working on applying this algorithm in practice, and I'll also briefly talk about the real production usage in the later part of this talk. So what can we get from differential privacy? In this part, we will mainly consider central level differential privacy. Well, the central level differential privacy will protect that model won't memorize each individual user's data. Remember, in federated learning, the clients won't share their data. Their local data are private only to themselves. They won't share this data with other clients or the server. Furthermore, with central differential privacy, the trained model won't memorize each individual user's data. And let's see, the differential privacy is a nice complement to federated learning techniques. How can we get differential privacy? Let's start from the basic algorithm, which is one of the most popular used algorithm, particularly in practice. This is the federated averaging algorithm. In this algorithm, in each round, the server will send a global model to each clients. The clients will train this model based on their local data and send back their model updates. Then the server will aggregate these updates and use it to update the global model. There are various variants of the federated averaging algorithm. And what we consider here is like differentially private federated averaging. The main algorithm is similar. You made two changes. One is that before clients send back their updates, they will limit each user's contribution by doing some clipping. And this is what we do for bounding the sensitivity for differential privacy. And then after server aggregates these updates, it will also add some noise proportional to the sensitivity when combining these updates. By those two techniques, you can get a differentially private model in federated learning. However, as you know, these techniques may potentially hurt your performance of the model. And the privacy utility trade-off of DP-Fed averaging algorithm heavily depends on this assumption that each device participates with probability Q. And this is called amplification by sampling for differential privacy. On the right-hand side, I show a simulation curve on Stack Overflow. The x-axis is the user level epsilon, which is used to measure the differential privacy protection. The smaller, the better. The y-axis is accuracy for utility. The higher, the better. As you can see, we show two curves. One is with amplification, another is without amplification. There's a gap, and the amplified version clearly has a win. But in practice, for cross-device federated learning systems, it's really hard to control this sampling. As we know that we have a lot of criterions for clients or mobile device to join the training. Most of them are some local criterions, like they have to connect it to Wi-Fi, they are being charged, they are not being used for other applications. Then they will probably join the training for this round. These are all client initiated. Due to this, we have other considerations like a lot of clients are non-overlapping. It's hard to get the same clients in every round. And it's difficult to know the exact size of the active population. Some clients are in the population, but for the entire training process, they may not actually participate in any training rounds. Then there are other techniques from the system side that is hard to apply in this. So it's basically what we are trying to say is that due to all the system constraints, it's really hard to do this random sampling to get amplification for federated learning. Some of our colleagues designed a protocol that allows you to do local client sampling that can be used for privacy amplification. But that one requires very complex changes to our current system. And this amplification also depends on large number of available devices, which is not always true during the training process. So let's go back to this curve showing the privacy utility trade-off for amplified and non-amplified DP-Fed averaging algorithm. Can we achieve similar privacy utility trade-offs without sampling? The answer is yes, and this is what we show with our differential private federated differential private follow the regular as leader algorithm. As you can see, the blue curve is the results from the paper. Let's dive into some details about what exactly this algorithm did. This is a high-level overview. Let's go back to the federated averaging algorithm and the variant DP-Fed averaging. Here, when we use DP-FTRL algorithm in this framework, the first part is still the same. We still do clip client updates clipping to control the sensitivity. The main change is second part. Instead of adding noise each round, the server will add noise proportional to sensitivity following a tree structure. So one of the main observations that lead us to this algorithm is that consider the model training process, not limited to federated learning, the general model training process, and we use Fed averaging as an example. Each step or round can be written as a prefix sum of gradients and updates, and the gradients updates in these prefix sums are the only one that are data dependent that should be privatized. And let's go back to DP-Fed averaging. In each round, we will add an independent noise. And once the noise is added, it will always exist in this prefix sum. And in DP-FTRL, we add noise based on a tree structure. And in each round, the aggregated updates can be considered as the leaf nodes of this tree. And whenever you can get whenever this leaf tree that lives in the same subtree, you only need to add one noise to the root node, and that's for this prefix sum. And one observation is that this tree structure and adding noise like this correlating noise in a particular round, some of the noise in the previous round added will be canceled out. That's a very simplified version, just give you some intuition. Let's say in practice, what you care about is the total noise added for both DP-Fed averaging or DP-STD algorithm and versus DP-FTRL algorithm. If we consider amplification, if we consider the algorithm without amplification, there's a square root n factor there. If with amplification, it's a constant 1 over epsilon, and the DP-FTRL gave us log n over epsilon. note that all this ignores the constant. So the constant also matters in practice. There are some follow-up work from my colleagues that can further improve DP-FTRL for these constants. In practice, when we apply this algorithm, we also consider other tricks. One is the Honaka trick to reduce the variance. And then we use momentum for optimization. And one of the a very important one is like when we have a multi-pass algorithm, basically if a client will participate several times, we will limit the number of the client participation to get a strong differential privacy guarantee. With the tree aggregation algorithm is basically stateful. You have to know the previous states. When we do the implementation, we only track the states of the noise instead of the states of the prefix sum. We need some memory consumption to maintain the tree state, and you can find the open source implementation in the repository. So let's look at some simulation results. Again, we have briefly seen this curve before. For like the strong privacy guarantees, when the epsilon is small, DP-FTRL is competitive with DP-Fed averaging with amplification. Remember that amplification is almost impossible in real FL systems. And when the epsilon is relatively large, at this regime, DP-FTRL outperforms DP-Fed averaging. And it's always better than DP-Fed averaging without amplification. Another thing we want to show you is that with some moderate increase in computation, specifically here, the number of clients per round, the DP-FTRL can outperform the DP-Fed averaging algorithm. So we use 4 times number of clients for the dashed blue curve. Why we are interested in these results is like this is one of the key observations we used to get formal differential privacy in practice. We rely on this hypothesis like for sufficiently large data, the utility accuracy will not drop if noise multipliers and the clients per round proportionally increase. Okay, now let's look at what exactly we did in practice. Here we do some here we train a RNLM model for next word prediction for Spanish language model in Gboard. The model parameter is 1.3 million, and we train for about 2,000 rounds over 6 days. Each round, 6,500 devices participate. And we configure each device to participate in training at most once every 24 hours. We release the privacy accounting for the multi-pass DP-FTRL in the open source repository. It's based on a dynamic programming version that can both handle some nuance in practice and being efficient to get a tight differential private guarantees. Note that the model size is not particularly large. It's about 1.3 million. This is one of the challenge in practice for mobile devices training, that a lot of times it's really hard to scale the model to a large number. But we are still a large scale problem. As you can see, we have a lot of mobile devices, and in each round we have 6,500 devices participating in training. Okay, so let's look at what we get from this production training. To our knowledge, we have the first production neural networks trained directly on user data announced with a formal differential privacy guarantee. And what are the guarantees we get? We get the DP guarantee for epsilon delta DP. We get epsilon 8.9 and the delta of 10 to the negative 10. And this DP-FTRL algorithm, we can also use the ZCDP. We also have a ZCDP accounting. The number is 0.28, 81. So how can we interpret this result? Let's see the epsilon delta bound. We get a single digit epsilon, which is less than 10. This is this is often considered a reasonable number for practice. And for the ZCZP, note that we have 0.81. And if you are familiar with differential privacy research, the U.S. Census Bureau for their survey, their ZCZP is about 2.6 or about that number. So our ZCZP bound is much stronger than what they used. So moreover, not only the DP guarantee is strong in this case, we also improve the model quality compared to previous DP fat averaging results. In the second part of the talk, I will talk about another problem we observed in practice, which is a periodic distribution shift and some preliminary results we have with multi-branch networks. And this is mainly based on our iClear paper this year. And we have open source code for this project also. This is a practical observation we found. This is a trending curve. The x-axis is the number of days. The y-axis is the network prediction accuracy. And this is trend in real cross-device federated learning system for a few days. You can observe that the trending curve has some oscillations. Let's zoom in a little bit. And these are the observations. Here, we actually trained 3 curves. One is the model trend for all times, the red curve. Another one is the blue curve that is a model trend only during nighttime. And the orange curve is a model trend during daytime. You can see that we have oscillation in all 3 curves. Another observation is that there's a gap between the performance of model trend during nighttime and the daytime. The gap is not always consistent. Sometimes the gap is large and sometimes the gap is smaller. The model trend with all-time data is more similar to the model trend with the nighttime data, but usually outperforms that the model trend with only one mode of data. This is an interesting observation. So what can we say about it? We actually don't know exactly what caused this oscillation. One conjecture we often consider is that in this cross-device federated learning system, because of the criterions for clients to participate in training, the one that we talked about before. So some of the mobile devices will more likely to participate in training during their local nighttime. But we have devices that are located in different time zones. So their nighttime are different. And then there are some periodic distribution shift of the mobile devices that cause these oscillations. In previous work, they model this as a block cyclic shift. So you will have 2 modes of the client distributions. One is for the night mode, another is for the daytime mode, and you will do a block cyclic shift. In our work, we kind of consider this as a smooth transition. If you look at the curves on the second row, by doing this smooth transition, by model this as a smooth transition, the curves are more similar to what we can observe in practice. But basically, this is what we can get from the simulation, and exactly what happened in practice is an open problem. Okay, so we model this. We model the periodic distribution shift with some smooth transition. And we don't know exactly what's the shape of the distribution shift in practice. So we introduce a parameter P to control the smooth transition, the shape of the transition. Note that by introduce a parameter, we can simulate different distribution shifts, but this parameter P is unknown to the extra algorithm we used to handle the distribution shift later. Okay, now we ask another question. Can we do better than federated averaging under periodic distribution shift? We introduce a multi-branch network to handle this periodic distribution shift. In this multi-branch network, we use shared representations for sample efficiency. And we have lightweight branches so that even for on-device training, it's still acceptable. We introduce a feature-based mixture model or clustering model module to predict the branches for this multi-branch network. Note that this module does not require labels for unseen clients. How can we train this multi-branch network? If we just do clustering or do mixture models in a federated training process, make some modifications for fed averaging, it turns out to be pretty hard because of some of the reasons are like intrinsic ambiguity from heterogeneity and the client sampling of each round. Remember, we talked about like in each round, like only a small portion of the clients from the total population will participate in training. And for different rounds, it's very likely that there's a small overlap between the clients. So this is hard. How can we deal with these challenges? For this specific problem for the periodic distribution shift, we introduce a temporal prior. This is like these periodic distributions give us some difficulty, but also give us some advantages or some priors we can use. So specifically for this problem, we know the peak time of each mode. And we know that we will smoothly transition from one mode to another. So based on this, we developed two algorithms. The first one is called FedTKM. We named it FedTKM because the mixed model is based on k-means clustering. So basically, we incorporate a k-means clustering module into the multi-branch networks and train the module together in a variant of federated averaging. If you look at this let's see, we further introduce a distance scalar alpha to shift the boundaries between the clusters. This is how we incorporate the temporal prior in this algorithm. To update this distance scalar alpha, we only need some aggregated results. Let's see the ratio of assignment for each cluster on each client to update this alpha. The basic intuition is that this scalar is used to control the distance to each clustering centers. Remember in k-means clustering, how you assign a sample or a client in this case to a cluster is by finding the smallest distance to that cluster center. Now, if you have extra scalar, this will be used to adjust the distance so that you can adjust the size of each cluster and force it to move smoothly from one mode to another. We further develop another algorithm. Instead of k-means clustering module, we use a Gaussian mixture module. Why we have two algorithms is like, well, sometimes this GMM module is more powerful, because of how you parameterize the model and how you update this model. But that the GMM algorithm also needs a lot more information to estimate the parameters. The FedTKM algorithms only requires aggregated results to update model parameters. But the FedTEM algorithm, which is GMM based, need parameters from each client. And on the server side, we will rank these clients. We will rank these parameters for clients and use it to update the GMM parameters. So the size of a parameter we get from each client is not large, but getting like non-aggregated results still make it hard for us to be compatible with the existing differential private algorithm and the secure aggregation algorithm that we have to provide stronger privacy guarantees in federated learning. So the FedTKM use a scalar to estimate the periodic distribution shift. How well does it work? We show an example on CIFAR. The first figure on the top is the ground truth periodic distribution shift we have. And the second row is the estimation by using only the aggregated results to update the model parameters, k-means, clusters, and the scalar parameter alpha. It did a pretty good job at least for this data set. Let's look at more simulation experiments. We have 3 data sets. For each data set, we have 2 modes, and we have periodic distribution shift from one mode to another mode based on a smooth transition. For EMNIST, one mode is the 10 characters version. Another mode is the 62 characters version. For CIFAR, we switch between CIFAR 10 and CIFAR 100. For Stack Overflow, we switch between question and answers. And we have some baselines to compare to. This cyclic SGD baseline is the one I mentioned before that assumes a block cyclic structure. We have some clustering approach, previous clustering approaches in federated learning for clients. Now there are some recent EM algorithms developed in federated learning. One note is that a lot of these clustering and EM approaches, they assume that you have access to labels on some unseen test clients. Basically, they are more like a personalization approach. For those algorithms, we often have to use a variant of the algorithm. We either providing ground truth labels or using confidence instead of losses. Let's look at the results for EMNIST. We vary P to simulate different distribution shift patterns. Note that this P is unknown to our algorithm FedTKM or FedTEM. And we show the strong baseline of Fed averaging when uniform sampling can be used, which is the citing without periodic distribution shift. A lot of baselines are without using temporal information can struggle that when the periodic distribution shift is presented. The 2 proposed algorithms are efficient in this case when we have access to temporal priors. We have more results on CIFAR and Stack Overflow. The observations are similar. One notable thing is that for Stack Overflow, FedTEM can be better than FedTKM. And improving all these algorithms is an open problem, and we encourage you to explore this interesting research direction. Okay, the last part of my talk, I will talk about heterogeneity in federated learning. This is based on our recent paper for theoretical understanding of heterogeneity and a benchmark with open source repository. This is a motivating example on heterogeneity. Consider we have a linear statistic model. Here, W star is a global model that can do linear for this linear statistic model, and the C represents the different clients. I represents a sample on a client. We assume that a single global model works reasonably well for different clients C. And how to train a global model in this case? We formulate a regression objective. On each client, we have a local objective FC, and it's a regression loss. And with some math work, you can get a formulation looks like this. Note that due to the data heterogeneity due to different X and the different number of samples on each client, different N on different client C, you will have different local minimizers for each local objective. In previous work, a lot of theory largely depends on this heterogeneity assumption measured by gradient dissimilarity. If we work out the math for this specific problem, it looks like this. It's the average of the square of the norm of BC. And if you look at the BC formulation above, if the variance is very large, or if you have a specific shape of the data, this BC can be quite large. But if you look at the convergence of Fed averaging for this specific problem, it's actually pretty fast. So there's a gap between what the theory tells us and what happens for Fed averaging in practice. Are we using the right heterogeneity assumption? So our observation is that this previous heterogeneity assumption is probably too pessimistic. And in practice, Fed averaging performs pretty good. We introduced the new heterogeneity assumption, which is measured by the average drift at optimal. By doing some evaluation for a few benchmark data sets, here I show EMNIS and the cycle flow. We can see that the new heterogeneity assumption is relatively small compared to the gradient dissimilarity we used before. And another observation is that this average drift at optimal measurement rho is consistently small during the training process, and it's irrelevant to the number of local steps. Even if you have a lot of local steps, the average drift at optimum is not that large. So based on this new assumption and the observations, we develop convergence rates for federated averaging. I only show the result for strongly convex and the local gradient descent here. We have more theorems and extensions for, let's say, general convex and the stochastic gradient descent in the paper. So basically, we can show that with this new assumption, federal averaging algorithm can be faster than mini-batch SGD. Especially the communication round of federal averaging is good, much better than what previous paper can show. Again, we assume that our analysis extensively uses this observation that the average drift at optimum rho is small. What if this number is actually large? What if average drift at optimal is large? We believe that in that case, that means a single global model that is very hard for a single global model to perform good for every client. In this case, we may need something that's beyond a single global model. One example is personalization. When we do personalization, each device will use all clients, they will use their personal, their private data to further refine the model so that each client each client will have their own model to do predictions for their future data. For this one, we recently developed a benchmark with various data sets and quite a few algorithms based on algorithm here. We consider 4 data sets for cross-device federated learning and 3 data sets for cross-device federated learning. We consider baselines of just local training without global models using Fed averaging plus fine-tuning. This turns out to be a very strong baseline, all doing clustering approaches in the heterogeneous society. And we present this benchmark with diverse tasks and strong baseline algorithms. And we have some interesting findings about this. I will only show this big table here to show you what we have done. There are a lot more experimental results and the descriptions of insights and the open problems for the federated learning about federated learning personalization in the paper. Yeah, so we have put the paper on archive. It may show up like in this week. Some interesting observation is that we all besides, in addition to the insights and in addition to benchmark and the baseline algorithm, we also have a lot of discussions on open problems, and some of them are particularly related to the practical concerns we have for various algorithms. For example, for Fed averaging and the fine tuning based on federated averaging, it is difficult to tune hyperparameters, particularly for a global set of hyperparameters. And some clients may get their performance may be hurt by the fine tuning approaches. And for hyperclustering, sometimes it's hard to train due to mode collapse. And it's quite difficult to interpret the learned clusters. Okay, so I'll do a brief conclusion. The federated learning system and research are interdisciplinary and quite challenging. We have a lot of practical concerns like communication efficiency, data heterogeneity, computation cost, and privacy and security. That being said, although there are a lot of challenges, there are also a lot of opportunities, particularly in co-designing algorithm and systems under constraints. We show that differential privacy can be applied in practice to complement federated learning to protect users' data. There are a lot of interesting work still to be done for this differential privacy plus federated learning. And we are very interested in various federated learning theories that can get practice, particularly the theories developed under certain practical constraints. So if you are interested and want to know a little bit more about what the constraints we have and what the federated learning system particularly for cross-device federated system looks like, I would encourage you to look at some of our white papers. One is this Advances and Open Problems paper in federated learning. And the second one is a field guide to federated optimization. So I will stop here and please, if you have any questions, feel free to ask.
Okay, all right. Thank you, Dr. Xu. Okay, so any questions from the audience? Okay, can you please come here? All right, thank you.
Hello, Dr. Xu. Thanks for the great talk. Yes, so my first question is possibly a bit naive. So in your first work, you apply a algorithm called DP-FTRL. So basically FTRL is known as a online convex optimization method. However, for the federated pipeline, there seems to be lack of role of the online optimization. So how is that related? Or in another word, how do we do FTRL in federated learning setting? Thanks.
Yeah, this is a good question. So basically, we name it DP-FTRL because we get the inspiration from FTRL about how we interpret the model updates instead of looking it as like each time you get a model updates or get a gradient, you apply it to the model and get to the previous model and get a new model. We view it like you start from the initial model and use a prefix sum to get a new model. That's why we name it DP-FTRL. About the online versus like federated learning question, is like I think this is probably not a question that's limited to federated learning itself. It's probably the question in general for machine learning. So in some sense, online citing is more practical, but it's a lot of times depends on what kind of like optimization algorithm paradigm you have. In some sense, like I mentioned, in federated learning, because we have limited control of how clients can be sampled, some perspective from online learning may actually help in federated learning setting. But I definitely agree that it's relatively unexplored direction, and I will encourage people to think about it.
Okay, thank you. So my second question is regarding the differential privacy. So basically, differential privacy has been a topic that have been studying in machine learning for a long time. So to my best knowledge, it seems that when applying differential privacy in deep learning, if you want to guarantee some epsilon delta differential privacy, then it means that you have to inject a lot of noise in deep learning. And maybe the accuracy, maybe in some benchmark data set, it will be very, very low. Like in CVPR, if you want to guarantee an epsilon delta differential privacy, the accuracy might be like only 60% or 70%. So so I was wondering if you have any like practical experience on this kind of trade-off under the federated learning setting. Like is it the same story as the normal training? Like if you want to guarantee some epsilon delta local differential privacy, then the eventual accuracy of the global model will be very like small or something like that. Thank you.
Yeah, thanks for the question. I think that in general, the privacy utility trade-off is true, and that's a big topic for any differential private algorithm. But on the other hand, there is a general trend that people have been talking about is that if you have enough data and if you have enough computation resources, and if you are willing to pay that to get a differential private model, you can get a reasonable trade-off, or in some sense, a strong differential privacy guarantee without hurting much of the utility. This is what we showed with our DP-FTRL work and the practical application for training G-bar language models. Basically, we rely on use a lot of computation resources. Like say we have a lot of clients per round. And another comment is like, even in general centralized machine learning, there's also a trend now, like by utilizing some public pre-training and use a very large batch, a lot of computation resources, you can get good performance. There are some recent papers on both language models and image tasks like ImageNet. Feel free to connect with me offline. I can send you with a few paper pointers if you are interested in this topic.
Okay, thanks for the explanation. Thank you.
Okay, are there any other questions? Okay, so Dr. Xu, for the last piece, you talk about the benchmarking. So for those machine learning algorithms, specifically for the deep neural networks, what kind of networks are considered in the benchmark?
Let me quickly show that again. So basically, we consider various applications for different tasks. For image tasks, we consider convolution neural networks and also one version of mobile net. For like language tasks, we consider LSTM and transformers. That's mainly for the cross-device sighting. The model has been specifically to be constrained as a little bit small compared to what we usually have in a centralized sighting. And similarly, we have various models for cross-silo sighting.
So like for the vision task, still I see a lot of literature in the federal learning. Seems like people don't use those large models like ResNet, not even using ResNet 50, or maybe just doing a couple of layers of network in their experiments. Do you have any insight on this? Or have any thoughts on this? Like why can we using, didn't see much of that work only using large models, in the federal learning literature?
Yeah, I guess one important thing we probably want to discuss is like we want to really differentiate cross-device and cross-silo sighting. For cross-silo sighting, if you have a lot of computation devices, let's say if each client is an institution, you will likely have a lot of resources. I don't see a reason why you don't want to use a large model. Mm-hmm. For cross-device FL, like if let's say if the clients are mobile devices really have limited computation and memory resources. So sometimes we are constrained by that. But even for that, we are considering using ResNet, just not ResNet 50, maybe a smaller version of ResNet. Yeah. And how can we but again, we are still in a large scale sighting in the sense that we have a lot of mobile devices. How can we use these mobile devices to collaboratively train a large model is a very interesting research topic people should consider.
Yeah, okay, all right. Okay, all right. Thank you again for the great presentation. I really appreciate your time and connecting with us. Give this awesome talk. Thanks again. All right.
Thanks for inviting me.